All right, welcome to Notes 9.6. Today we're going to talk about dilations and we're going to talk about symmetry. So let's begin, as always, with vocabulary. A dilation is a transformation that stretches or shrinks a figure to create a similar figure. You remember that similar figures have proportional sides and they have congruent angles. So that's what we're talking about here with our dilation. Since dilations create similar figures, they have a scale factor. And just like when we talked about our similar figures before, a scale factor of a dilation is the ratio of the corresponding sides of the image and the pre-image. When the dilation is a reduction, it shrinks the figure, and the scale factor will be between -1 and +1. So essentially it's a fraction. Okay, a fraction that is less than 1. An enlargement, therefore, is a growing dilation, and the absolute value of the scale factor will be greater than 1. So it'll either be a positive number greater than 1 or a negative number less than -1. One thing you may notice about these notes is there's no place where it talks about the properties of dilation. So I'm going to expect you to figure out what those properties are as they relate to whether or not it's an isometry and what the orientation is between the image and the pre-image. Okay, so we've been asked to draw a quadrilateral ABCD with the following vertices, and I've already sketched it on my coordinate plane. And you'll remember from when we talked about translations that we can use matrices to represent coordinate figures. So when we have a quadrilateral, we are going to have a 2x4 matrix. So I'm going to go ahead and I'm going to write in the coordinates into my matrix down here. So I'm going to do A in the first column, so that's 2, 0, and B goes in the second, 6, -4, and C is 8, 2, and then D is 6, 4. And then the way we represent the dilation is we multiply it times this scale factor. And when we do matrices and we multiply them times a number, we call that a scalar. And this time our scalar is 1/2. And all I do is I take every single coordinate and I multiply it by 1/2. So 2 times 1/2 is 1, 0 times 1/2 is 0, and so on. So we get 3, -2, 4, 1, 3, 2. And those are the vertices of my new figure. So I'm going to go ahead and plot those. All right, so I've got it plotted now, and you'll notice that my new figure is smaller, which is what we expected because our scale factor was a fraction, so it was less than 1, so we expected it to shrink, and every point has moved towards the origin because we were dilating about the origin. And that's basically how a dilation works. Now, I didn't have to use a matrix to do that. I could have definitely just multiplied every coordinate of every point by 1/2, and I would have gotten the exact same results. But we just want to show you that you could do it with a matrix if you wanted to. Okay, so dilating is not that difficult of a concept, and I think you probably have it by now. So I'm going to go ahead and let you work this problem on your own, and then I'm going to check for your answer in the notes check. We're also going to do all of those constructions that are in your notes that deal with dilating not on the coordinate plane. We're going to go ahead and do those in class tomorrow. All right, new topic, which is symmetry. And in this class, we talk about line symmetry, we talk about rotational symmetry, and we talk about point symmetry. So let's go ahead and define those and their related terms. Line symmetry, a figure in a plane has line symmetry if the figure can be mapped onto itself by reflection in a line. So basically, if I can fold it along a line and it maps all the points map back onto themselves, then my figure has line symmetry. So obviously, when a figure has line symmetry, there is a line of symmetry, which is that reflection line, that fold line that I was just talking about. So when we talk about rotational symmetry, we know that a figure in a plane has rotational symmetry if the figure can be mapped back onto itself by a rotation of 180 degrees or less. Obviously, every figure, when rotated 360 degrees, has rotational symmetry, so that doesn't count. So it has to be 180 degrees or less than that. And it needs to, as you rotate it, it needs to look exactly like the figure you began with for it to have rotational symmetry. If a figure has rotational symmetry, then it has a center of symmetry, which is the point of rotation for that rotational symmetry. So it's the point about which the figure rotates. So that is different from point symmetry. Point symmetry is a type of rotational symmetry, and it means that the figure has a rotational symmetry of exactly 180 degrees. Now it can have a symmetry or rotational symmetry of less than that, so 30, 60, 45, 90, right, all of those, but it means that also when you rotate it 180 degrees, it maps back onto itself. So that is point symmetry. All right, so let's talk about the number of lines of symmetry and how we draw them. I'm going to go ahead and let you look at A, B, and C here, and I want you to pause the video and draw the lines of symmetry and write down how many there are, and then we'll come back and we'll talk about it. A is a rectangle, B is a regular pentagon, and C is an irregular pentagon. So go ahead and do that and pause the video now. Okay, so for a rectangle here, you should have gotten that there are 2 lines of symmetry. There is a horizontal line and there is a vertical line. I didn't draw that very well, but you get the point. For our regular pentagon, you should have gotten 5. There's a line of symmetry through every vertex that bisects the opposite side. And since there's 5 vertices, there are 5 lines of symmetry. And that's generally how it's going to work in regular polygons. You're going to have the same number of lines of symmetry as you do vertices or sides. Now, in our irregular pentagon, there's only 1 line of symmetry, and it is straight down the middle. If I try to draw any other kind, my figure's not going to map back onto itself. Did you get them right? If not, do you understand what you did wrong? Fantastic. Okay, let's talk rotational symmetry. Why don't you look at these 3 examples here, the square, the regular hexagon, and the kite, and you tell me if they have rotational symmetry, and if so, tell me what the degree is that will map it back onto itself. So go ahead and do that, hit pause, and come back when you have an answer. All right, so our square does indeed have rotational symmetry, and it is 90 degrees. Every time I turn this 90 degrees, it's going to map back onto itself. Same thing for our regular hexagon. It has rotational symmetry, and it has a rotational symmetry of 60 degrees. So every 60 degrees, 60, 120, 180, and so on, it maps back onto itself. Our kite does not. Right? I have to rotate it all the way back around before it looks like itself again. So it does not have rotational symmetry. So from these first 2 examples here, I want you to be thinking about how you get rotational symmetry from the shape of the figure. Okay, let's talk about these next 4 figures. Here we're getting fancy. We have all kinds of funky things going on. We've gone away from polygons now, and we're just talking about all different kinds of figures. And we need to identify what types of symmetry it has. So, as a reminder, it could have line, it could have rotational, it could have point, and it could have some combination of those, or it could be none of the above. So why don't you do 1, 2, 3, and 4, and see if you can figure out which kinds it has. If it has line, tell me how many lines of symmetry. If it has rotational, tell me what the rotational symmetry is. And then, obviously, if the rotational symmetry includes something that is a factor of 180, it would also have point. So go ahead and do that. Hit pause and come back when you have an answer. All right, so number 1 here, it has line symmetry, and there are 4 lines of symmetry. It has rotational symmetry of 90 degrees, which means that it also has point symmetry. Number 2 here, it has line, and there are 6. It has rotational, and that is 60 degrees, and it has point also because 180 is a multiple of 60. For number 3 here, gets a little more complicated, but it still has line, and there are 8. It has rotational of 45 degrees, which means that it also has point. And then oddly enough, these two are exactly the same when it comes to their symmetry. And I want you to try and figure out why they are exactly the same and be prepared to talk about that in class. All right, last 3 down here at the bottom, we need to figure out if it has the rotational symmetry that they've asked about. So does my kind of nuclear fusion thing down here, does it have a rotational symmetry of 120 degrees? It does. It very closely resembles a hexagon. And we know that hexagons have a rotational symmetry of 60 degrees, and 120 is a multiple of 60. All right, how about Pac-Man? Does it have 180 degrees? Well, no. If we rotated Pac-Man around 180 degrees, then we would not get him with his mouth open up here again. So this one does not have, not only does it not have 180 degree rotational symmetry, it doesn't have any rotational symmetry at all. And then my star here, my fancy pants star, does it have 45 degrees? Yes, it does. It is essentially an octagon. It's got 8 vertices, so it does in fact have rotational symmetry of 45 degrees. And that's how rotational symmetry works. Okay, so dilations and symmetry, not that difficult. Please come prepared tomorrow in class to do some cool activities with them. And if you do have any questions, be sure you ask when you see me. All right, thanks.